Sir, sorry to interrupt you at once. So, just have a quick question about the transformation matrix. So, when we try to write the transformation matrix and try to, we get the image, right? So, from the domain to the codomain space. So,
Yes.
when we try to write the transformation matrix, we write the entries as columns. So, what happens if we write the entries as rows instead of writing them as columns? Or is there any speciality between the two?
Uh, so the thing that allows you write it as columns, you get a general expression. Anyway, this thing I'll explain maybe at the end if we have time. So we are
Yeah,
already,
sure.
this is this week 9 session, so it's not. Uh, so the convention is there for a reason. So that is the short answer. And what that reason is, I'll tell you at the end.
Okay, okay.
Okay, so yeah. Now we start out with multivariable functions. Multivariable functions, certain examples of this you have already seen. So in linear algebra, what are the kind of functions that you dealt with? Functions of the form v to w satisfying certain properties. Now, those v and w could be some Rn and Rm or some abstract vector space, but in the case that it is Rn to Rm, so this is a function which takes n tuples as the input and m tuples as the output. Now, not all functions are linear, as we have seen some x, y, and stuff like that. So, analyzing functions of that form, functions of the form f from Rn to Rm, which need not satisfy any linearity property, because linearity gave us a lot of power in the sense that we could express every vector in terms of finitely many vectors. We could express transformations also as just, if you knew the transformation on a finite set of vectors, then you knew the whole transformation and so on. But that is not the case in general. The functions that you encounter in general will be far more uh, it, linear structure is too much of conditions to expect from all functions that you encounter. So we will do analysis on general functions of the form f from Rm to Rm. What do I mean by analysis is you have to, the calculus of variations. So the rate of change of the function as we vary something. Whatever you have learned in Math 1 probably for one variable functions, we will try to see it in the multivariable setup. So what's a one variable function? It's something of the form, I'll just call it D. This is a D is a subset of R to R. Some example is just something like f of x is equal to x squared plus x plus 1. So this is what is called a polynomial function. Or you could have other things as well, trigonometric functions, logarithmic exponential. You have seen many properties like sum of functions is still a function. And so whatever we are discussing in the multivariable setup, one way to relate to what is happening is look at the corresponding notion in the one variable case and why we are doing certain things differently than the one variable case. If you try to understand that difference, you'll see a lot. I mean, partial derivatives and all that cannot be, I mean, it doesn't make sense to define in the one variable case. We will be doing it in two or more variables case. And what were the things that some of the terms that you saw were limits, continuity, derivatives. Now, why were derivatives used? Like give me one application of derivatives.
Finding maxima minima.
Yeah, so finding maxima and minima. So what do you think of when you are given a function of one variable which gives you a one variable answer, meaning a function from R to R or a subspace of R to not a subspace necessarily, a subset of R to R. You are looking at some quantity which is dependent on one parameter. But in general, you could have things depending on more than one parameter, correct? Physical, you can just take things from physics and you'll see what I'm talking about. Let's say resistance. Resistance is a function of, let's say, voltage and current, or you can think of human body mass index is a function of height and weight. And all these things, they depend on two or more factors. There are functions which depend on two or more factors. And over here, it is straightforward to think about minima, maxima, and all that. So what is the value of x for which your function attains a maximum value or minimum value? This is what you would like to see. Similar things we'll explore. And first, we'll set up some basic terminology in this session, and limits, continuity, and all those things we'll see in the next session. And over the course of the next 3 weeks, we'll see generalizations of all this. So now, in general, you don't need a function from R to R. You can have multiple inputs. Let me just call it Rn to Rn, Rn to Rn. Now, such a function is called of this form. These names are not something that you need to commit to memory. It's just, it's naturally named, so it's fine. Vector valued multivariable functions. So if m is equal to 1, then, so why is it called vector valued multivariable function? So the value of the function at a point, where does it lie? What is the codomain over here?
Rm.
So it's Rm. Rm, the space Rm we have
Yes,
seen
sir.
as a vector space, right? So even without looking at the vector space structure of it, Rm you call n tuples or m tuples as vectors. So that is why it's called vector valued multivariable function. Then f is called a scalar valued multivariable function. Why? What is the codomain in this case? If m is equal to 1, then it is just R. R is the set of scalars. So it's called a scalar valued multivariable function. And a scalar valued one variable function is just a one variable function that you know from before. So let's just take examples. Something like R2 to R. F of xy is equal to xy. Now it depends both on x and y. And yeah, this is a polynomial function actually, x times y. If you are given the input x comma y, the output is x times y. This is a trivial example. And linear transformations. So if t from Rn to Rm is a linear transformation, that is by definition a multivariable function. Let's say inner product spaces you have seen. Let's take the standard norm itself. What is the domain and the codomain for the standard norm?
Rn to Rm.
Yeah, into
So this is also a multivariable function. It takes as input a vector in Rn, let's say, and it gives you the distance between that vector and the origin, or the length. the standard norm. Okay, so these are a few examples. If you want something like, okay, this is in general, this gives you a vector valued multivariable function. In general, if you have a vector valued multivariable function, let's say f from once again Rn to Rm is a vector valued multivariable function. Then f can be written as f1 up to fm. So what does that mean? What is f of xy? F of xy, not xy in this case, it is x1, x2, and so on up to xn. So where will this be? The codomain is Rm. So this will be an M tuple, right? So I can write this as f1 of x1 up to xn, fm of x1 up to xn. Each of the components of the image of the function at a particular point, that will be a scalar valued multivariable function. So to make this clear, let me just complete this first. F1, Fm are called the components of it. Now, if I have, let's take a linear transformation itself from R2 to R2, where xy goes to our favorite guy, x plus y, x minus y. Now, the image of each point has two components. One is x plus y and one is x minus y. So here, I just call this T1. Maybe this is not the best notation, but let's just work with it for now. So what can you see about each of the components? Each of the components is a scalar valued multivariable function. And there is nothing specific about 2 or it being a linear transformation over here. If you have a function from Rn to Rm, the image of each point will be an n tuple. And if you take just one of them, that will be a scalar valued multivariable function. So many times we don't work with vector valued multivariable functions, but we just work with scalar valued multivariable functions. And whatever we have to deduce for vector valued multivariable function, we'll just say if the components satisfy whatever property we require, then it is true for the vector valued multivariable function as well. So many times you'll see that the examples we see will be just using scalar valued multivariable function, meaning the codomain will be just R.
So how to differentiate between them?
So the codomain will be given to you, right? So vector valued multivariable function, you will be given components. You will be given as many components there are. If there is only one component, then it is just a scalar valued multivariable function, and it will be in order. So the first component will be this.
If codomain is Rm, then
If codomain is Rm, what is the question?
like if codomain is Rm, the our function will be vector valued or scalar valued.
If m is equal to 1, it is scalar valued. If,
Okay.
if m is greater than 1, it is vector valued. This is just a name and not really something that you need to worry too much about. I mean, in that sense, R is also a vector space. So even a function from Rn to R, you could call a vector valued multivariable function. The general thing is vector valued multivariable function, but scalar valued multivariable function is reserved for when m is equal to 1.
Okay, sir.
All right.
And sir, if n is equals to 1 and m is not 1, like f from R1 to Rm, then what if
Yes.
it is called vector valued single variable function?
Yes. Yes. It is a vector valued single variable function. There are when it is not a the entire R. Even if it is an entire R, it is fine. It is also called a curve. But yeah, all these names you don't need to worry too much about. And yeah, you can refer to whatever the prof has used and just stick with it. This will not be very ambiguous, or there will not be any issues regarding the names of the things. All right, so things that you know already: domain, codomain. Already you have seen the domain and codomain of these examples. Now let us talk about range for a bit, maybe, which will lead us to surjectivity and injectivity. And on to which is surjectivity, right? So suppose you're given the expression for a scalar valued multivariable function of two variables, which is f of x y is equal to 1 by x square plus y square. Now the domain in general is a subset of some ambient Euclidean space. So defined on an appropriate domain, let me just call defined on D, which is a subset of R2. Now, for D to be a valid domain, what are the conditions? What is the condition?
X and Y should not be 0.
Denominator should not be 0.
Yeah, the denominator should not be 0. X and Y should not be 0. You can make it slightly more rigorous. So it
But
should not be
if
simultaneously 0.
yeah,
Right. So if 0, 0 does not belong to D, then D is a valid domain for F. So what's a valid domain is just where the expression makes sense. So if the denominator is 0, it doesn't make sense. So that's what we have to watch out for. And okay, just as an extension of that, let's just call this guy something like this. So let me ask how many points, or describe the set.
It's the circle x square plus y square equals 1.
Describe the set that has to be removed from R2 to obtain a valid domain for the above. The answer is already given.
So all points on the circle x square plus y square equals 4.
center at origin.
Yeah, so this is just the set, I'll call it S1, which is x comma y in R2, such that x square plus y square is equal to 1. And you know that x square plus y square is equal to 1 is a circle centered at the origin with radius 1. Okay, so now that we have that, what is the codomain of this? That will be R, because I have not specified the codomain. That's fine. Let's assume that the codomain is R. But what is the range of this?
Range will be from -1 to R plus.
What is -1 to R plus?
Means infinity plus infinity.
Range of F. Is everyone okay with that?
No, sir, please explain.
No, I'm not even saying that it is correct. Does anyone have any other guess?
The denominator should not be 0, right?
I'm just asking code.
I'm asking the possible values that this function will take.
0 can be excluded here. -0.
Minus infinity to -1.
Wait. So this was guess number 1. This was guess number 2. And then what was it? Minus infinity to
-1.
minus infinity to -1.
I mean, it won't take infinite value. It would be 0.
Then that would be 2 because you take -1 would be the lowest value. So -1 to infinity and you exclude the 0.
So what's the guess? What's the candidate?
I mean, in my view, it should be -1 to 0.
Yes, -1 in closed bracket and 0 in open bracket.
-1 in closed bracket.
And yeah, 0 is
Zero
not
in open
approachable,
bracket.
but near to 0, wherever it is. Yeah.
Yeah, it should be -1 to infinity actually, with minus in 1 as a closed bracket because it can be -1. So -1 till infinity.
Oh,
But 1 upon infinity will approach 0, no?
x square plus y square minus 1 would always be greater value than that.
X square plus y square should be greater than 1.
Okay, you guys can discuss.
I mean, if you apply the limits for the max values, denominator would become higher, and then that value would become near to 0. I mean, the two limits that I can think of, x square plus y square, could be 0. That makes -1 as one value, and then it can go only above than that because x square plus y square would be a positive value.
I think it can approach minus infinity, right? Say, for example, x square plus y square, let it be like something like 0.25, 0.00 something. That will be like a -1 plus 0.5, say, for example. So that becomes something, if 1 by that value becomes infinity, right? Like minus infinity, something it will go. So,
Something
yeah,
like
yeah.
so minus infinity
you
is
want
possible.
you want something like this, correct?
Yeah, correct.
And then what would be this? F of xy at such a point will be what?
It tends to minus infinity.
So this would be something like -100.
Yeah.
So the only option that survives is this guy so far. But then -1, we can see that -1 is taken. -1, so this is also not correct because -1 is there in the range for sure. When at the origin, the value, what is the value of the function?
It's -1. So we have to make it as close to -1.
Okay. So when you look at the points on the domain, they can be any value from R2, except that circle. So we are excluding that circle. But think of this as your domain R2, and we have excluded this circle. So there is definitely, we have to see what happens at the origin. And if you look at, let's say, a point in between radius 1 and radius 0, or at between the origin, the same behavior is followed by every point over here, right? It doesn't really matter what angle I take it in, because x square plus y square is just the radius. Is that clear what I'm trying to say?
Yes, because the locus remains the same, right?
Yeah, so if I take a point like 0.5 or 0.5, I'll get the same value, or anything over here which has the radius 1 by root 2. Or half, actually, not 1 by root 2, just radius half. So this thing is symmetric under rotation, this kind of thing. Even if you don't understand points close to, at 0, the function value is -1. And as I approach the circle, as one of you guys noticed, what is the value? What is the nature of the value?
Tends to minus infinity.
Yeah, so it tends to minus infinity. So it's something like you have a minus infinity to -1. Every possible value is taken. So it goes in this way as you move away from the origin. And what happens? And this minus infinity is at the circle of radius 1, which we have excluded, of course, for obvious reasons. Now, what about the behavior outside the circle? So what happens close to the circle, and what happens as you move further and further away?
It decreases. It decreases.
So what's the behavior close to the circle?
It attains infinitesimal value there, and then it suddenly sharply decreases.
No, you're just above the circle, or you're just beyond the circle, outside the
As we
circle.
go outside, it tends to 0 because x square plus y square
Yeah, but where does it start?
at -1. It starts at -1 and then
No, the point over here is something like at a radius 1 plus some small number, right?
So it will be very high. The function value would be very high.
The function value will be very high because I can take something like 1.0001, and what happens to an xy which is at radius 1.0001? At such a point, the function value will be very high. This will be 1 by 0.0001.
yeah.
10,000. And of course, I can make it as large as I want by going as close to the circle as I want. Is this point clear?
Yes.
Yeah. And as I approach infinity, or as I go for a larger and larger radius of circle, you will get something like x square plus y square minus 1. But this guy is as large as you want. So the denominator being large means the function, how does it behave?
It goes to 0.
It tends to
It
0.
goes to 0. And it always remains positive. So what is the range finally? The range. These are the wrong answers for people referring to these notes. What is the range equal to? Does this make sense?
Yes, sir.
Yes, sir.
So I'll give this as an exercise.
Sir, but I have a question here. So when you write 0 to infinity, so here 1
Just
is
1 minute.
included, right? One is possible.
1 is included, yes. So what is the value of x and y? Give me one value of x and y such that f of xy is equal to 1. This would imply that 1 by x square plus y square minus 1 is equal to 1.
X is equal to root 2, y is equal to root 2.
Root 2, root 2 will work. So any point on this circle of radius root 2 will work. Root 2
No, it's
will not
0
work.
root 2.
Root 2,
0,
0
comma
will
root
work.
2 or root 2, comma 0. Yeah.
This
Yeah,
will
it should
work.
be root.
I've just rearranged over here, so I
Yeah,
get x
so
square
it should
plus
be
y
root
square
2
is equal to
0 or
root 2.
0 root 2. Yeah.
Yeah, those computations are fine. You can take care of that. But the point is that one is also taken. Is that okay? For this week 9, 10, 11, GeoGebra 3D is extremely useful in visualizing. So you can, even when the sessions are running, I would say just have it on the side. Once, whenever we are discussing whatever example, just plot the graph. Just plot the graph and see the behavior and relate it to what is being explained. That will improve your understanding by, yeah. It is almost unfair to not do that to yourself. So that's that. So now you got to know what range and this thing are. So one-to-one and surjective, injective and surjective are whatever you have been studying. Injective is f of xy is equal to f of x prime y prime. I'm just doing it for two variable case, but it's the same thing. Or okay, let us before doing that. In general, x tilde will be used to denote this n tuple wherever this domain is. Now, if f of x tilde is equal to f of y tilde, then this should imply that x tilde is equal to y tilde. Now, you cannot check preimage of 0 and all that in this case because we are not assuming any linearity. So in this case, you have to check this itself. Are there two vectors whose image is the same? So let us just look at this example itself. Is this an injective function?
It is not injective.
No.
It's not.
Example?
We
I
can
mean, it's
just have
very
any
easy.
values and then replace that with minus x minus y. So still x comma
Yeah.
y.
Yeah, you can do f of xy is equal to f of minus x minus y, or xy not equal to 0, 0, of course. That's fine. That's just, I'm just being pedantic, but that's okay. Or in fact, other than one point, every element in the range has infinitely many pre-images. Is this a statement that everyone understands?
So please repeat the statement.
Yeah. Let me call this guy as example something. So the function in example this, there is only one point in the range finitely many pre-images. Read the sentence and tell me if you understand. Is this understood? So you take any point in the range. What is the preimage of that point? So as you observed over here, f of xy is equal to f of minus x minus y. This will also be x minus y. So what is the thing that combines all of these observations? So take for example f of xy is equal to, I want 3. What are the preimages of 3? This is asking what are the xy that satisfy f of xy is equal to 3 is the same as asking what are the preimages of 3.
We can
So
always
that would
form a circle, right? Like with that point.
exactly. So whenever you look at the preimage of any number within the range, you will set up an equation like this, and that would be I did not want this. I wanted something else. Let's say 4 1 plus 9. I guess this will be better. I'll just do 4 by 5. So when I have x square plus y square minus 1 is equal to 5 by 4, or x square plus y square is equal to 9 by 4. So what is this set of points x square plus y square is equal to 9 by 4?
Circle with center 0, radius 3 by 2.
Yeah. So this is circle with center 0, radius 3 by 2. Now there's no reason for this to work specifically for 4 by 5. Whatever point you take over here, if you take f of xy is equal to, let's say, c naught. I'll just take an arbitrary point. What is the equation that will be set up? X square plus y square minus 1 is equal to 1 by c naught. X square plus y square is equal to 1 by c naught plus 1. And what is this? This is just a circle with center 0 and some appropriate radius. Now, of course, this would not have worked if 0 was in the origin, right? C naught, I could, if I had one, but we are saying that this point C naught is in the range. And as long as that happens, this will have infinitely many solutions, except for one point. What is that point?
-1.
C naught is equal to -1, or
C naught is equal to -1.
Yeah, that's it, right? F of xy is equal to -1. So what happens when C naught is equal to -1?
0.
X square plus y square is equal to 0. And how many points are there which satisfy x square plus y square equal to 0?
Only one. The origin.
There's just one, which is the origin. It's a sum of two positive numbers, so each of them has to be 0. But x square equal to 0 implies x is 0, and y square equal to 0 implies y is 0. So apart from this one guy in the range, which is -1, everything else is a circle of positive radius, which has infinitely many points. Is that okay? Is that fine?
Yes, sir.
Yeah. So here, f is not injective. But yeah, coming up with injective functions is not that difficult. If you have something like f of x comma y is equal to, you will not have scalar valued functions which are injective. You will have them, but those are difficult to construct. But you know what injectivity is. You have to see if there is any point in the range which is the image of two different points. And surjectivity is similar. F in example dagger is not surjective. Why is it not surjective? To show that it is not surjective, what do you have to produce?
Range should
That
not
the
be
range should be equal to the codomain.
Yeah, in this case it is not. So what is the set of points which are not there in the range?
Open -1 to close to 0.
Zero.
Yeah.
Yeah.
So if instead I can write this function from R2 minus the set that I called S1 to R minus, what was it? I think it was open -1, closed 0. So if this function is surjective. Is that fine? So of course, whether something is surjective or not depends on what your codomain is. If you take the codomain equal to the range itself, then automatically it's surjective.
Being surjective also like implies that the inverse of the function exists, right?
One of the inverses, either the right inverse or the left inverse. I don't remember exactly which one. It should not be very difficult to figure out. What is the way that I can come back? I can go and come. It should be precomposing it with it. I think it is f of g. Something like this exists.
F of g should be equal to the g of f, and that should be the identity, right?
But that you will not get a two-sided inverse. But then it would become then it would become bijection. This is not a bijection.
Yes.
Yeah, in this case, it is not injected.
Yeah. So it's anyway not bijective.
So you can get something like f of g is identity on. I want to do this. Yeah. You can get a g such that this happens. A g from this guy, r minus this, to wherever. Just send it to R2. It doesn't matter. Such a thing exists. So this is whatever, right-handed inverse or something. You can find something like this, but this is not part of the syllabus, so I'll not let me not specify that. So when it is surjective, you get one-sided inverse, and when it is injective, you get the other. So you will have a both sides inverse you will get if it is bijective. In this case, it is not. So you will not get both sides. You can just take it as an exercise for yourself. And then you have.
Sir, excuse me, sir.
Yeah.
So I had a small doubt. I'm just using GeoGebra for the first time. So what happened? The expression you gave, I was trying to plot in GeoGebra. I could not do it. Means I gave the expression, they are not showing anything.
What did you put in?
The 1 by x square plus y square minus.
So make sure you're on GeoGebra 3D, first of all.
Okay.
And then do this. Type in this.
Okay, got it. Okay. Thank you.
Then let me know if it works.
Thank you.
Sums, products, quotients. Quotients will work only when the denominator is non-zero. And what else? Compositions, whenever applicable, are multivariable functions. So this is not really much of a statement. So I'll just explain it verbally. So if I have something like f of xy is equal to x square plus y square, and then I have f of g of xy is equal to x plus y. I can add these two to get something called f plus g of xy, wherein the output at every point will be the sum of the outputs. So it's like x square plus y square plus x plus y. I can do products for scalar valued functions because otherwise product of two vectors is not something that you know. So, or not something that is there. So products only for scalar value, and quotients also you can do. Suppose you want to do quotient for this. So if you want to do f of xy divided by g of xy, what is the problem that you'll run into? That this cannot be defined everywhere.
At g of
Where
x,
can it not
y,
be defined?
but g of g is not, g is equal to 0. That's where it would be defined.
At that point, it cannot be defined, but can you describe that set geometrically to me?
Yeah, see y equals minus x, straight line.
Yeah, yeah. So if this is your domain, you will have to exclude this point exclude this line y is equal to minus x, and then this will be a valid function. This is a valid function on the domain, which is the two half planes, which lie on the either side of the line y is equal to minus x. That line itself should be excluded. All right. So that's about, and compositions, you know how to take composition of functions. Now, let me talk a bit about visualization. At some point, maybe I'll do a session using GeoGebra.
So just a quick question here. So like if you're given some certain complicated functions, for instance, let's say some arbitrary functions of the form x cubed by x square plus y square minus some polynomial function.
Okay,
So,
okay, some p of x, g of x, something, yeah.
Yeah, so
You,
there's some polynomial function in both numerator
yeah.
and denominator. So, and you were asked to compute the range of this function. So, I mean, at times
Unless
it
it is
becomes
very
complicated.
straightforward, you'll not be asked
Yeah.
that because it's not.
Mm.
I mean, there is no algorithm to compute everything. Uh, the range or what points to exclude even if I give you something like x square plus xy plus 3y square, something. Okay, maybe this one you can think of uh, something. But in general, this is still at least a conic, right? You may be able
Yeah.
to analyze this. But then if I do something like x to the 10, y to the 10, what are you going to do? Like what are even the roots of this? Sure, you'll have one 0, 0 as one of the roots, and you
Yes,
say that
that's right.
I have to remove 0, 0 from the set. But then of course it's not guaranteed. There is no way to compute. Even if I give you something like a one variable polynomial, something like x4 plus 4x cubed plus 19x plus 3, something like this. Can you do this? You cannot do this. Not by hand. So there is no general method to determine what are the points that you have to exclude, or then even if you know what the domain is to find the range, there is no general method. But even if we want to test you on things like that, it will be simple things like this, where the domain enjoys a certain property, and the function is defined in such a way that it's doable. Only there it becomes a reasonable question. Otherwise, it is not. And you will be asked reasonable questions for most part. Okay, as I was saying earlier, whenever we talk about anything in multivariable setup, what you need to do is go back to one variable case. So what is the visualization of a one variable function? So how do you see a one variable function? Let's take an example itself. So if I give you f of x is equal to x squared, what is the first term that comes to your mind?
Parabola.
Yes, I was hoping it would be that. So this is parabola, right? Why is it called a parabola? As in, what about it is just symbols, right? F of x is equal to x squared.
Yeah, because it will have two roots and it has it's a polynomial.
So the thing is that the graph of this is a parabola. Now, what is the graph of a one variable function? If you plot on the x-axis the input and on y-axis the output, then the graph that you get, assuming that it's going through the origin, this thing is y is equal to f of x. So what is and this figure is what is called a parabola. It's not this function that is called a parabola. The function has a graph which is a parabola. Now, What is a point? What is a generic point on this graph?
X comma x square.
Yeah, x comma x square. On this line, of course. So you know that points of the form 2 comma 4 are there, and points of the form, let's say 3 comma 6 are not, right? You should have x comma x square. So 3 comma 9 would be there, but 3 comma 6 would not be there. So it does not belong to graph. So as a set, the graph of the function f, sometimes this is also used. The symbol is not very important. Sure, if we are using the symbols, we'll tell you what it means. What is this as a set? What is this as a subset of R2? This is the set of all points x comma f of x such that x is in R, or in the domain wherever you want it to be. In this case, the domain is R itself. If you collect all the points of the form x comma f of x, that set is called the graph. And why is it called the graph? Because you can actually visually plot it. Now, what happens in the case of multivariable functions? What happens to the graph of a multivariable function? What does it mean to say the graph of a multivariable function? There are issues. One is that human imagination does not go beyond 3 dimensions. We have already used up 2 in one variable case itself. So the things that we can plot and analyze properly are functions of the form R2 to R, or R to R2 also, but we'll stick to R2 to R. Now, for every xy, I'll get an f of xy. So what would be the graph of a two variable function, scalar value two variable function? If I were to extend the same notion from the one variable case.
With the x, y, and f of x, y.
So it's xy, f of xy, as xy varies in R, or the coordinates vary in R2. Now, what is this a subset of?
R3.
R3.
So this is a subset of R3. Remember, this is a subset of R2. So we take as many variables as there are in the domain, and as many variables are there in the codomain, and the sum of those two will be the space in which the graph sits, or the space which the graph is a subset of. Right. So once again, to understand, let's try plotting the graph of f of xy is equal to. So this is where your GeoGebra will
So
do.
please scroll down little. Yes, okay.
Yeah, this is where your GeoGebra will do a much better job than myself. So I will try my best. So this, what would be points on the graph of this function f? It would be of the form x, y, x square plus y square. So two of the coordinates, x and y, will be allowed to be free, and the third coordinate will depend on the value of x and y that I take, right? So let's say this is my x, y, and z. Now, if I want to plot the graph of this, I need to take an arbitrary point on this plane, on the xy plane, and look at the height that I'm assigning to that point will be actually equal to the function value. So does this graph pass through the origin?
Yes.
Yes. Yes. X,
So
x, y, 0.
So because 0, 0, 0 plus 0, which is just 0, this is in the graph. Now, if I look at, let's say, the circle of radius, I don't know how to draw a nice circle, which is slanted. So assume that this is the circle of radius 1 in the xy plane. So these are all points on the domain, right? What should be the point on the graph above any such point? It would be of the form x comma y comma 1. On xy belong to S1.
Okay, so this circle
S1
is
as
of
before.
radius 1, right?
Circle is of radius 1. So suppose that this is 0, 1, 0, this point, and this point is 1, 0, 0. And this is a circle in the xy plane. I cannot make it look planar unless I really put some thought, effort, and dedication to it. But no, let's just assume that this circle is in the xy plane and look at the points above it. So the part of the graph that will be above it will be in the plane z is equal to 1. Is that clear?
Yes, sir.
And similarly, as you reduce the radius, you will get circles of smaller radius until you hit the origin. But it is not proportional to the radius, it is proportional to the radius square. So what you get, this you can check, is something of this form.
It will be like inverted cone, right? Like with that apex.
It's not a cone, it will not be pointed, that's the thing. So
it's the parabola, right? Paraboloid, right?
It will be a paraboloid. It will be like a parabola and you're rotating it about the z-axis. Think of it that way. Because the radius of the circle depends on the square of the radius and not actually equal to the radius. So test this, check this on GeoGebra again. If you want the cone, what you'll have to do is f of xy is equal to square root of x square plus y square. And this is just equal to radius. Just saying. So if you don't understand what this r is, it's fine. So the
Here,
graph of
here your
f
your
will
r
be
is
the
around
cone.
circling around the z axis, right?
So I'm just saying for a point xy, r is its length or the radius of the segment, the circle which this point lies on, will be an inverted cone. Once again, you should check this. With apex at origin. So did that work? Did z is equal to this work? Is the person still around or no?
Yes.
Okay. So you do the same thing. So now you know why the z is equal to f of xy sort of expression works, right? Because you're specifying that the z coordinate cannot be anything. It has to be the image of image of xy under the function f. So this is how you can visualize two will be very useful. Spend some time, get used to the code or whatever in GeoGebra. It's not really code even. It's just click the relevant functions and it will give you visual representations ready. So I think professor uses capital gamma of f. So just verify what he means. Symbols, whatever you use, it's fine. So that's about the graph of the function. Now we'll come back to the earlier motivational question that we were discussing, that we would like to analyze minima, maxima, calculus of variations in general. In the case of a one variable function where the graph is a curve in R2, something like this, whatever your one variable function, the graph is. So what was the thing that allowed you to talk about minima, maxima? What give me that particular points of interest.
Double differentiation would be negative for a maxima and double differentiation would be positive for a minima.
Yes, so double differentiation, you're one step ahead. First of all, the things of interest are critical points. Now, what are critical points?
So if prime x is 0.
Where the yes.
Derivative is 0 gives me points of interest. Now, what happens at the derivative at the point where f prime x is equal to 0? What is the tangent line? Let me call it
It's
that.
parallel to x-axis.
Parallel to the x-axis.
Yeah. So what happens when it is parallel to the x-axis is that your thing curves down or it curves up. So that is when you will definitely get straight lines. But straight lines can arise in other situations also, like the saddle points. Whenever you have something like this, even then you'll have your derivative to vanish, but it will not be a minima or maxima. But if it is a minima or maxima, then and if it is differentiable and all that, your derivative will vanish and there will be a tangent line which is parallel to the domain, right? We have to keep this sort of thing in mind and try to set up the theory in the multivariable case. So what is the first hurdle? So if you want to do something like this, if you want to say something like this, what is the first obstruction, obvious obstruction?
Continuous and different.
No, I give you a multivariable function, and you have to do some differentiation. Do you know how to do it?
Yes, I'll take the derivatives, partial derivatives with respect to the
variables. You may know it, but we all of us don't know it yet. So here, if I have a one variable function, something like this, I just keep using simple functions over here. I know that the derivative of this is this. And how do I do it? How is the differentiation of a one variable function defined?
N into x to the power n minus 1.
That is the ready formula, but what is the first principles approach? So suppose I want to find derivative at x naught.
Limit, I mean, a plus h minus a, function of a plus h minus a by h.
Limit as h goes to 0,
yes,
f of x naught plus h minus f of x naught divided by h. So this is what is the instantaneous change of the function, not just the instantaneous change, the rate of instantaneous change of the function. So one way to think about it is if I'm traveling, let's say from point A to point B, if I know that the distance is d and the time that I take is t, what is the speed of your travel?
d by t.
That would be d by t, right? That is just distance by time. Now this will give you some speed. Speed I don't want to call it s. I'll call it v, but v typically is for velocity, but fine. So if I have some v, which is d by t, but that does not mean that at every point I was maintaining that speed, right? I just know the value about the first thing and the last thing. So there I call the speed as v. I just take the numerator to be the distance and the denominator to be the time, and then I get what is average speed. It's something like average speed. But if I want a more precise value of how much speed there is at a particular point, what I need to do is I need to reduce the time of observation. Now, if I get some d prime by, I suppose I look at only until this point. Then I get a new d prime t prime. And at every point, I get a value of a distance and value of time. And then I take this d, whatever d by t as a d of t as a function of t. And then if I take the limit as t goes to 0, that means I'm taking a smaller and smaller interval every time. And the limit of that value, that would be what is your instantaneous speed. Right? It's the same thing. The derivative is just motivated by that. What is happening over here? The value of the function at a time, let's just call it time. It is just the variable x over here. The value of the function at a little bit after x naught. If you want to observe the instantaneous change at x naught, you look at what's happening at h time after x naught, and then look at the difference. From a point of reference, if you want to look at what is happening at x naught, you'll see this is x naught and this is x naught plus h. And what is the difference between this? That is just h and the corresponding function value. What you're just doing is distance by time, but here it does not necessarily need to be distance. You're looking at function value at h time after it and subtracting it from the initial value and looking at the time difference. You're looking at function difference divided by time difference and then letting that difference go to 0. And that would give you instantaneous change of the function, the rate of change of the function at that point. That is the limiting value of change in output divided by change in input. Now, this is all in one variable case and you very well know it. Coming back to our multivariable things, I will most of the time explain things in just f of x, y. The same principle will hold in higher dimensions as well. Scalar valued multivariable functions, just remember that. Now, if I want to see, okay, let me just draw this one more diagram. If you look at it in terms of the graph, what happens? So if I'm at some point, f of x naught plus h would be something over here, and that h would be this. And as I go closer and closer to x naught, which means I'm taking smaller and smaller intervals of observation, the limiting value would be the tangent at that point or the derivative. But what happens in the case of a two variable function? What step do I take? So what is so the domain in this case the domain was just the x-axis. In this case, the domain is the xy plane or some portion of the xy plane. Suppose I'm at some point x naught, y naught, and I want to observe the rate of change of the function at this point. In the case of a one variable function, at a point x naught, there is only one direction to go. Of course, there's the negative of that as well. But that's the same thing. X naught plus h takes care of both of them. If you approach 0 from the negative side, then you will get the other side as well. So there is not much not much change in direction, right? But how can I approach, or what is the h that I can change? Like if I want to observe the rate of change, I could look at a point h over here, a point h over here, or there are infinitely many directions, right? The step that I take in order to observe the rate of change of the function, that could be in any direction. Do you understand the problem?
Yes, sir.
Yes, yes.
Yeah. So there is no f of x
Sir, you're muted.
Yeah, I think we lost him.
Hello. At what point
Yes.
did I disconnect?
Sir, actually, the point is that we do not know which direction to move because there are infinitely many directions.
At that point, I stopped. Is it? I got disconnected. Is it?
Yes.
Yeah.
Okay. Sure. Just 1 moment. Let me continue from there. Yeah. All right. So yeah, we have infinitely many directions to move over here. But taking motivation from the fact that we have n variables, we'll just look at what happens when we change the function by changing only one variable. So instead of change of f in general, we look at change of f in the x direction. Now, what does that mean? I alter the value of f by only changing the x variable by some h amount and measure the change. What I get is f of x naught plus h comma y naught. So y naught we are not changing at all. In terms of the domain, we look at this direction wherein we keep the y naught fixed, but x naught is allowed to change. Is that okay? So this is your change in output. Now this, as usual, has to be divided by the change in input. If you want to know the rate of change, you want to measure how it changes with respect to the change in the variable. And then we take the limiting value if possible. Of course, there are functions for which this cannot be done. But wherever it can be done, this quantity is called the partial derivative of.
So it is the thing here, right?
Sorry.
H quantity is the change.
Yes.
Okay.
So that change is what we are making tend to 0.
Sir,
Why is it
in
called
which,
partial derivative? Yeah,
sir,
go ahead.
one question. So, in which functions h cannot be assumed to tending to 0?
You can take something like 1 by xy at 0, 0 if you take something like that. Okay, let's take examples later. So partial derivative of f with respect to x is equal to this whenever the limit exists. To understand it, at least for me, it is very natural to just think of it as the rate of change in the x direction, which means I move in the x direction by some amount, I divide by that amount, and whatever that amount is, that we take limiting to 0.
So this simultaneously not becoming 0, something that we saw in the earlier example, that won't work here, right?
What is simultaneously becoming 0? Which one?
Earlier example, I remember, vaguely remember that you're saying that x and y can't simultaneously become 1 or something, so that the denominator will become 0 or something.
Oh, but that is for this one. Was it this x square plus y square minus 1,
Yeah,
1
yeah,
upon
yeah.
that? No, that is for the definition of the function itself.
Got it.
But here you cannot take the partial derivative at a point which is not on the domain. So you'll take it somewhere inside. There again, all of this will hold still.
Okay.
Whatever you have discussed so far, that will hold still.
So what is the difference between derivatives and partial derivatives?
So derivative, we would like to call something as the derivative. We have not defined the derivative yet for a multivariable function, but that should capture the entire change of the function, right? This is the change of the function only in a partial direction. Like we are just doing the analysis with respect to one variable. So that's why it's called partial derivative. Partial with respect to x. Now partial with respect to y would be similar. You would just say f of x naught comma y naught plus h minus f of x naught y naught divided by h.
So that would be like that would be claiming
We
to
are looking
be
at only one.
left and right differentiable, right?
No, because if when you change with respect to y, you are looking at something like this. You're looking at the change of the function along this line. Remember that this is not this is the domain. XY plane is the domain. My points over here are all on the domain. So here you don't have right hand and left hand because in one variable case you just have two directions. You have one direction. So you can take negative and positive of that direction. But in this case you have infinitely many directions. So you'll have to specify it in a different way.
So HY is like a plane.
XY is the R2 plane, and that is where our
So
function takes values from.
So if it's a plane, then how do we find the tangent?
So yeah, the tangent will come in the next week. We'll discuss it then. So that is where we are going in some sense. We identified the point that generally you cannot define a derivative of a two variable function just by mimicking what we have done in the one variable case. Just by taking f of xy plus h doesn't make sense. So we added that h only to one of the components and called it the partial derivative with respect to the first component. Now the same thing will happen for n variables. You can just change one component. Let's say you change the ith variable, that is called the ith partial derivative of f, or the partial derivative of f with respect to xi, if xi are the variables. So the notation for this is fx, okay, f subscript x. There's fx, there's fy. Now let's do an example. Let's do the same thing. F of xy is equal to x square plus y square. This is a two variable function, scalar value two variable function. Now find fx at 1, 2. Let's do something. Without knowing anything else, if I were to do this using just the first principles.
Why?
So this is fx at x naught, y naught. The formula is this. Okay. This may be not required over here. I'll just write it over here. So what is fx at x naught, y naught? The rate of change of f at the point x naught, y naught in the x direction. That is what this symbol means. Now over here I have f of xy is equal to x square plus y square. What is fx at 1, 2? What is the quantity that you have to take the limit of? Can someone say?
F of x would be x square plus 2.
Just one moment. Just take it step by step. We want at 1, 2, you want to measure the change in the x direction. So you do something like this. F of 1 plus h, 2 minus f of 1, 2 divided by h. Is this okay? Why I did this? Compare it with this.
Yes.
2 is the result, is it?
The answer is 2, yes. But let's compute the whole thing. So we want to see if this has a limit as h tends to 0. So we just use the formula 1 plus h square plus 4. This is f of 1 comma h, 1 plus h comma 2. This is the first term, minus 1 square plus 4, or 1 plus 4, just write that, divided by h. Did I make a mistake? No, I did not. So what do I get if I simplify?
2 plus 4h.
Okay, 2 plus 4h. Is it 2 plus 4h? H. I think it's just 1 or 2 plus h. One plus h square plus 2h plus 4 minus 1 minus 4. So that is just h plus 2. Isn't it?
Yes, sir. Yeah.
Yeah. So what is the value of this as h approaches 0?
2.
This is limit as h goes to 0 of h plus 2. This is a direct one-dimensional limit. So the substitution will give you the answer over here. And that is 2. Is this okay?
Yes, sir.
Right. Now let's take another example. Something like f of xy is 1 by x square plus y square if xy is not the origin, and let me call it 0 if xy is the origin. So these are something called piecewise, some people call it piecewise defined function, where you define it in two different ways on two different things. So you cannot use the first formula 1 by x square plus y square to define the function at the origin, correct? You will run into a problem. So instead, yeah, it will be blowing up near the origin, but as long as you're not at the origin, it would still be valid. It will be arbitrarily large, but it's fine. But at the origin, you cannot use that. So you'll define it in a different way. This is similar to defining something like, let's say tan x. You can define tan x to be something like this, and then at the origin, maybe you can define it as 0. You could. It would not be continuous or anything, but it would still be a definition of a function which equals tangent in most points. Tan x. By tangent, I mean. Anyway, coming back to this thing, we define it as 0 at the origin and 1 by x square plus y square when it is not at the origin. So suppose I want to find out what limit of, or I want to find out fx at 0, 0. What is the thing that I have to calculate the limit of?
f of h comma 0,
h comma 0 minus f of 0 comma 0 divided by h. Now, can you simplify this and tell me what it is? F of 0, 0 is just 0. So it is just f of h comma 0 by h. But f of h comma 0 is just 1 by h square. So I get 1 by h cube.
Here you can't take the limit because it goes up.
Yeah. So here this limit does not exist. If I write limit over here, that limit will not exist. Therefore,
can we take the L'Hospital's rule here? I mean, L'Hospital's rule here.
It's not. No? It's not a 0 by 0 thing.
But it's can't we use that in 1 by 0 as well?
No, you need a 0 by 0 for that. If you have something like 1 by h, the limit, you know that the limit of 1 by h does not exist. It goes to infinity. But if you could use L'Hopital, it would become 0 by 1, which is not the limit. So,
yes.
Even over here, that would happen. But you know that as h goes to 0, 1 by h cube blows up. So here, partial derivative with respect to x or y, you can check this for y as well. It is the same computation, pretty much the same computation, does not exist. So that's why I was saying here, if the limit exists, there are functions for which the limit does not exist. How much time do we have? We have about 20 minutes.
Actually, I'm confused. Can you explain what a limit is? Because I haven't studied this topic for a while, so I forgot.
So the limit of a function is the real number that the function approaches as you approach that point. Okay. I cannot give you much more than that because it is understood to be a prerequisite for this course. But I'll just give you an example. Maybe it will bring back something from your previous course. Take something like x square plus 2x plus 1 divided by x plus 1. Let's say you want to know the limit of that as x approaches minus 1. This function as it is, if you substitute x is equal to minus 1 over here, what happens?
You will get 0.
It doesn't exist.
You get 0 in the denominator. So it'll become an indeterminate form. So as I approach minus 1, this function, this quantity x square plus 2x plus 1 by x plus 1, you cannot analyze its behavior as it is. So, but you can observe that this can be written as something like this. And at every point other than minus 1, you have this thing to be equal to x plus 1 itself. So what value does x plus 1 approach as x approaches minus 1?
0.
0.
0, right? So that is what the limit is. The function itself may not be defined. For a better example, you take something like sin x by x, and then you see why the limit of that is equal to 1 as x approaches 0. You look back at your one variable course and you'll find it. But at least this should be immediate, that as h approaches 0, as h gets smaller and smaller, what happens to 1 by h? Here it's 1 by h cubed, but what happens to 1 by h?
If it's approach 0, then it will become undefined.
It will become larger and larger, right? So there is no limiting value. It can become arbitrarily large. However, if you have something like 1 by h minus 2, as h approaches 0, what would this approach? As h approaches 0, the denominator approaches minus 2. So the whole thing approaches minus half. So we say that the limit does not exist when such things happen. When you have a form that does not have a limit, like 1 by h does not have a limit. This is very well known. And you can verify that by producing an arbitrarily large number. You can choose a small enough h to get as large a value as you want. And that is not something that should happen when a limit exists. Anyway, back to the regular multivariable stuff. So partial derivatives exist when the limit exists, and it is not always guaranteed to exist. Now, when is it guaranteed to exist, and all that we'll see. But this is not a very practical way of computing the partial derivative. So how do you actually, the practical way of computing partial derivative? Partial derivative is keep all other variables constant and differentiate. This is not, again, very precisely written. I'll tell you what I mean by that. So if I have something like f of x1, x2, x3 is equal to something log of x2 on an appropriate domain. I'm not saying that it is defined on all this thing. E to the minus x2 square plus x3 square, something like this, on some d in R3. Now find fx at all I need is the second variable needs to be positive, so that log makes sense. Suppose I want to find the partial derivative with respect to x1. So I need to specify, or let's do x2. x2 is better. Find the partial derivative with respect to x2 at the point 1, 1, 1. If you are adventurous enough, you can try doing this with the limit formulation, and you'll see how hard it is. You'll have to do something like limit as h goes to 0 of x1 square, or here it is just 1 square, right? It's 1 square plus log of 1 plus h plus e to the 1 plus h square plus 1 minus, okay, this guy is fine, minus log of 1, this is also fine, e to the 2 divided by h. You can try and simplify this. Maybe it's hard, maybe it's not.
So is the answer 2 plus 2e?
Let's see. Now, what does it say over here? Keep all the other variables constant and differentiate. So here, I want to find the partial derivative with respect to x2. So I treat other variables as constant. x1 and x3 I treat as constant, and I look at it as a function of just the variable x2, and I differentiate. So fx2 so the first term, what is the derivative of x1 square?
0.
Zero.
So this will be 0 because we are treating it as a constant. What is the derivative of log of x2?
1 by x2.
So this would be 1 by x2. And what is the derivative of e to the x2 square plus x3 square?
2x2 e to the x2 square plus x3 square.
So here, suppose you had e to the x square plus 1. How would you differentiate this with respect to 1? With respect to x?
2x e to the x square. So f
So
prime
you would
x
keep
and
e to the x square plus 1 itself, and then d by dx of x square plus 1. And that would be e to the x square plus 1 times 2x. Now the same thing we'll do over here, but instead of 1, we have x3 square. So this x3 square we treat as a constant. So first thing I get is just this times the derivative of x2 square plus x3 square, which happens to be 2x2. So the partial derivative of f of x2 at the point 1 comma 1 comma 1 would be 1 plus 2 times e to the e square. Is this clear? Is it clear what happened over here?
How did you get e square?
So I've substituted 1 for both x2 square and x2 and x3. That's 1 plus 1. So e to the 1 plus 1, which is e square, times over here also I substituted 1, which gave me this 2 e square.
Okay, got it.
Right, so this is quite simple. Just keep everything else constant, treat everything else as constant, treat that this is a one variable function, and the variable is whatever your variable of interest is, and then do your one variable differentiation. Of course, it's don't use when you have, let's say, piecewise defined functions. So when you have a well-behaved function like this, which does not have places where it vanishes or places where it is defined differently. And why is that? Is because of 0.
Yes, except at x equals to 0, x2 equal to 0, I think. So there it's not defined.
It could be no here
Because of the
even in
element.
this case the domain itself will be such that x2 is positive. So this will be something like r cross r plus cross r, something like this. The thing is that if you have something like, okay, check this is a very standard example. Xy divided by x square plus y square. This is a very well-known function. So over here, if you want to find the partial derivative with respect to x at the origin, you cannot just differentiate this. You cannot just differentiate this. Let's say if you want partial derivative with respect to x, you cannot differentiate this with respect to x, treating y as constant and then substitute 0, 0 in the whatever thing you get. You have to use the limit approach over here because it is not defined the same way at the point of interest.
Because it's of the form
Which is
0 by 0.
Yeah, so
If you have-
here, even if it
You
was
can use
something
L'Hopital.
else, yeah, you can try this. You can try this, but what I'm saying is you cannot differentiate this with respect to x and then substitute 0, comma 0. That is not allowed. What you have to do is do f of h, comma 0 minus f of 0, comma 0 divided by h. Take the limit. Only this works over here.
So this function is not defined at origin.
It is defined as 0, but it is not defined the same way as it is at the other points. As in, at the origin it is different, and everywhere else its behavior is different. So there, if you're analyzing things at the origin, you cannot use this methodology. But if it is defined the same way, well defined, well behaved in the point of your interest, then you can use this method where you just treat it as a function of one variable, the variable whichever you want to take the partial derivative with respect to. And yeah, that's about partial derivatives. Now coming back to our big picture, our domain, a point in our domain typically looks like this, and you have infinitely many directions to travel. But what we have done is just look at two particular directions, or in higher dimensions, n particular directions if your point is in n dimensions. What about the other directions? What about the change in the other directions? Does knowing fx and fy at a given point give complete information about the change of the function with respect to every other variable or every other direction? Is fx and fy enough? So that is where we'll define the more general definition of a directional derivative. The philosophy is identical. You are measuring the rate of change of the function with respect to change in the input in some direction. Now we have taken care of two directions. If I'm looking at it using the usual coordinates that we know, we have taken care of the direction 1, comma 0, and we have taken care of the direction 0, comma 1. All of this with the understanding that we are working with a two variable function. Similar things apply for n variables also. Now, if I have an arbitrary direction of the form u1, u2, what I need to do is look at what happens to the function as I move one step or h amount in that direction. So for a unit direction, u is equal to u1, u2. Look at the following. As usual, we take x0, y0, the point of interest. We look at how the function changes as we move h units in the direction of u, and then look at the change. We compare it to the original value and then divide by h. Now this is what we call the rate of change of the function f at the point x0, y0 in the direction u1, u2. Now since that is a mouthful, we call it the directional derivative of f at x0, y0 in the direction u. So here make note of the convention that we use unit vectors u. So you will, even in higher dimensions, we'll just use unit vectors. If I substitute, so 1, 0 is a unit direction, right? So if I substitute u is equal to 1, 0, what do I get? So substitute u1, u2 is equal to 1, 0.
Partial derivative along the x-axis.
Yeah. This is easy to verify. Just substitute partial derivative with respect to x. And u is equal to 0, 1 gives you partial derivative with respect to y. In general, you will have n of these. If you have a function in n variables, you will have n directions, like principal directions, something like the standard basis vectors. And the directional derivative in those directions are exactly the partial derivatives with respect to those variables. But here, directional derivatives are more general. Here, we can take 1 by root 2, 1 by root 2, or whatever, cos theta, sin theta, whatever your theta is. You can take u1, u2 equal to cos theta, sin theta, and you can look at the change of the function in that direction. What happens if I change the value of the function by changing the value of the input or changing the value of the domain variables in the direction of h, that is in the direction of u1, u2 by an amount h. That is what directional derivative measures. Now, examples for this and other problems and the remaining concepts of week 9 I'll cover in the next session, Thursday.
Sir, I have a question regarding this. So when you talk about these partial derivatives, about the directional derivatives, so aren't you taking the projection of those vectors along the direction you are supposed to measure the components of those vectors?
Could you repeat that?
So when you take the directional derivative, for instance, if I am taking this directional derivative in some sense, isn't it the projection of those vectors across the directions we are supposed to take? I mean, the components of the vectors across those directions we are supposed to take.
The projection of what? The projection as in the projection of vectors that we have studied? Is that the sense in which you're using it?
Yes.
So okay. Yes. So this is also denoted by f of fu at x0, y0. Of course, this is also if it exists. Okay. So what were you saying? Are you saying fu of x0, y0 is the projection of what?
So it's the projection of the vector that we took along the direction of u1 and v1. I mean, here it's
u took the projection of u onto
across x. So I didn't look into the vector. I think u comma v or something that you took the vector.
Where?
u1 and u2.
The projection of what on what?
Okay, so the projection of 1, 0. Okay, let's So projection of 1, 0 along u1, u2, and projection of 0, 1 along u1, u2.
Projection of 1, 0?
Yes.
Because then you just get u1, u2, right?
Yes, so aren't we doing the sort of same thing here? If we are taking because here we are also taking the standard basis, and what you are getting instead is the partial derivative with respect to x.
There is some thing to say about that. When we discuss the gradient, I'll tell you about it, but this is not the correct way to put it. I'll tell you what the correct way is in the next session. I think gradient is in the next session. So we'll discuss this then. But if you just say projection of u1, 1, 0 onto u1, u2, what is this? This is just this times this. This will be just u1, u2. And this is a number. This is not a vector. So it's not the projection of something. Do you get it?
Yes,
In,
yes, yes.
Why
Yes.
this statement does not make sense?
Yes, yes.
Yeah. We'll discuss this in the next session.
Excuse me,
And there
sir.
was, yeah.
Sir, is there any book for week 9 to week 12 to study for?
It's best to refer to the videos and the sessions over here because specific to the topics that are covered in the course, I don't think there's exactly a book, but what is that standard reference? Uh, I forget its name. There's too many editions also. Just one moment.
Is it
In any standard calculus book, you will find all of these topics. But sometimes we have, sorry?
what reference is like? Is it James Stewart book?
I think it is that one, yeah.
Okay. And yeah, I also want to ask about syllabus for the ET. Is it week
It's
1
all
to
weeks, week 1 to week 11, yeah.
and is there any particular weightage for 9 to 12?
9 to 12 is about 50%, and the first 8 weeks are about 50%.
Okay, got it. Thanks.
Sir, I have a doubt in quiz 2. Like, I'm not sure if it is discussed earlier in the session, but there was.
Let's take subject doubts first. If there are any, then we'll do that.
Yes.
Yeah,
Are
so
there
I
any subject doubts?
this direct like can you take differentiation current space using this directional derivative?
Could you repeat? I can't hear you.
Uh, can you measure the change in Rn
Is it just me, or can anyone else hear what he's
You're
trying to
not
say?
audible, Preetham. You have to.
can you hear me?
Yeah, I think now it's better. Yeah.
So I was saying, can we take like can we measure the change using directional
Oh,
derivative
no,
Rn?
I just lost you in the most important part.
Can you hear me?
Yeah, yeah. Go ahead.
Yeah, so I was saying that can we measure the change in Rn using this directional derivative?
Change in Rn? Yeah, this concept is nothing specific to just R2. What would happen in for a function in Rn to R? It has to be scalar value. So what you do is f of. So if you want to take a direction, let's say u1, u2, un, a direction would look like that, right? It would just be this minus this. Anything that I've discussed is not specific to the two-dimensional case. So you'll have something like this. This will, of course, make sense when we discuss directional derivatives, which we will do as in discuss directional derivatives by using examples, which is where we'll start the next session from.
Okay, got it.
Sorry, could you repeat why the h is still there for even when you have the directional derivative? I thought it was instead of h we are having now the directional derivative.
No, it's not instead of h. So over here, when we talked about partial derivatives, what we did was we changed only one direction, right? So this is nothing but f of x naught y naught plus h times 1 0. You can look at it this way.
Oh, okay. All right.
Okay, so you're measuring, you're taking your direction vector as 1 comma 0, scaling it by h. You're just measuring h amount in the direction 1 comma 0, and adding it to your input variable, looking at the output, seeing its change from the original value, dividing by h to get the instantaneous rate of change. Now you generalize this to a general direction where you use u1, u2. Instead of 1, 0, you use u1, u2. The h is still there. The h is there so that we can reduce h and get closer and closer to the function value. And that is how you look at instantaneous change. All right. Anything else? Okay, then. Yeah. What is the issue with quiz 1? Quiz 2?
There was one question like where A is similar to B was given, but when alpha value.
Yes, I am aware. I've seen the post also. I'm aware